So that's the piece of the class on sort of continuum plasticity stuff. And now for the rest of the section on plasticity, I want to talk about more atomistic mechanisms of plasticity. So what we're first going to calculate is a theoretical cohesive strength. So what's sort of a theoretical ideal strength of a material? And what we're going to find is that real metals, for example, real ductile materials that behave plastically, they don't have strengths anywhere near this ideal strength. And the explanation is that the yield strength is governed by the motion of dislocations. So there are defects in the structure. So let's start by looking at the theoretical cohesive strength. Let me get rid of this stuff. So you remember when we talked about the elastic modulus, we talked about the interatomic energy separation curve, and we differentiated that to get a force separation curve. And you can think of the force separation curve in terms of stress and strain. So let's just say that we can take the energy separation curve and differentiate it to get a force separation curve. And if we do that, we get a curve that has a shape somewhat like this. So say we take the force and divide it by an area. We take the separation divided by the initial interatomic spacing. We get stress versus strain. The curve has a shape somewhat like that. And we could think of this peak stress here as the ideal cohesive strength. So that would be the stress required to pull the atom apart. And it turns out that when you do this, you get a strain of about 0.25 there. So here sigma c is the cohesive stress required to pull the atoms apart. And that occurs at a strain of about 0.25. And then you can idealize this curve here to say the stress is equal to sigma c times sine of 2 pi epsilon. So you just approximate it as a sine curve. So obviously that's a very crude approximation. And then we can say that at a strain of 0, the slope of that curve is equal to the Young's modulus and we can get the slope by just differentiating this thing here. So if I differentiate that, I get 2 pi sigma c times 2 pi times cos of 2 pi times epsilon, and epsilon 0, so cos of 0 is 1. So this would give you an ideal cohesive strength of approximately the modulus over 2 pi. So the 2 pi is around 6.
Is that the radius critical, or what is RC?
RC?
2 pi RC? Oh.
It's a sigma, I think, yeah. I'm not quite sure where you're looking, but it's a sigma.
Oh.
Where?
That. Sigma.
This
Yeah,
thing?
yeah. I thought it was an R, sorry.
Okay, well, let me make it clear. Is that better?
Yeah.
Okay. Okay. And you can do the same thing in shear, so you could make the same sort of argument in shear. And in shear, you would have a similar expression, say, for a shear strength tau c, and instead of the Young's modulus, you'd have the shear modulus. So it's on the order of the shear modulus over 2 pi. And you can use more exact, you can use more realistic energy separation curves and get a better estimate. And if you do that, then you get the cohesive strength is, instead of 1 over 2 pi, it's something like 0.05 or 0.1 times the modulus. So we'll just say more exact estimates using more realistic energy separation curves. So something like 1/20th of E to 1/10th of E. And recall what we talked about earlier in class was that the yield strength typically occurred at a strain of 0.2%. So 0.2% means a strain of 0.002, and that means that it would be, the yield strength would be 0.002 times the Young's modulus. So, 2 over 1,000 instead of a 10th or a 20th. So there's a huge discrepancy between this theoretical shear strength or theoretical uniaxial strength and what people measure for a yield strength. And in the early 1930s, there were several people thinking about this and working on this, and they realized that dislocations and the motion of dislocations could explain this large discrepancy. So I don't know if we'll get there today, but today or tomorrow or Friday we'll talk about how dislocation motion relates to yielding in materials. Okay. So let's see. So I'll just say this is much lower than measured yield strengths. Oh, sorry, it's much higher. Oops. Sorry. What I meant is the yield strength is much lower than that thing. Much higher. Thank you. And so the yield stress corresponds to the stress at which dislocations move through the crystal lattice. Okay. All right. So let's see here.
Question. What do you mean by 0.002 E?
Oh, so remember how we said the strain at yielding was like 0.2%?
Oh. Okay.
That's So if that's the strain, the stress is just that times E.